Welcome back to Carneades.org. Today we're going to be continuing with our series, 6 months of set theory and higher order logic. This is month 2, looking at operations and relations. In this video, we're taking a look at what is the absolute union of a set. Now, a union is an operator in set theory. In this video, we are covering absolute unions, an operation on a single set or class that looks like this, the union of C. These are not to be confused with relative unions, which is an operation between two sets or classes that looks like this, A union B, which we covered in a previous video. So if that's what you're looking for, check out that video. If you're looking for the absolute version, though, let's go. So imagine you wanted to combine all the elements of a series of classes into one big class. You could create a long list of compound operators of all of those classes using union operations. You could say the union of E and the union of D, and the union of C, and the union of A and B. But that's a lot to say. Another way to represent this idea would be to create a class of all the classes in a list, and call that a class. Say F, the class F, equals, by definition, A, B, C, D, and E. Like just the class of those things. The absolute union of that new class, which we would represent as the union of F, of this class is the same as the union of all its members. So the union of F is simply equal to the union of A, B, C, D, and E. A union of a class is a new class that contains all the members of the original class. The union of F contains all and only the members of F, and therefore it contains all of the members of A, B, C, D, and E. And in other words, is simply a different way to state the union of A and B and C and D and E. Another way to think of this is that it eliminates one level of curly brackets from inside a class. So if G is equal to the class of H and I and the class of J and K, then the union of G is simply the class of H, I, J, and K. You see how we eliminated one of those sets of curly brackets from within G. If L is equal to the class of M and the class of N and O and the class of M, N, and P and the null set, then the union of L is equal to the class of M, N, O, and P, because those are all the members of L. Note that when we eliminate those curly brackets from the null set, it disappears, because there's nothing that is the member of the null set. And finally, if A equals the class of B and the class of C and the class of D and the class of the null set, then the union of A equals B, the class of C, the class of D, and the null set. Note that the null set doesn't disappear here because we've eliminated just one of those pairs of curly brackets. The set of the null set does have a member. It has one member. It's the null set. And so if the set of the null set is a member of A, then the null set is a member of the union of A. The formal definition of an absolute union that we will use is as follows. For all A and all B, the union of A equals B means by definition that for all X, if X is a member of B, if and only if there exists some Y such that X is a member of Y and Y is a member of A. In other words, for something to be the union of a class, all of its members must be members of some member of the original class. Or for B to be the union of A, all of its members X need to be the members of some Y that is also a member of A. And all of the members of all of the Y that are within A are members of B. Up next, we're going to look at what is the absolute intersection of a set. But first, give these a try, and we'll give you the answers at the end of the next video. So make sure you subscribe and hit that notification bell so you don't miss the next video and the answers. We have our class definitions. We've added a couple, and the exercises are as follows. Try to find the union of A, the union of B, the union of C, the union of D, and for a bonus challenge, find the union of A. For yesterday's problems, we have the following answers. So the intersection of A and C, first off, is just going to be C and D, also known as just C. If we subtract out D because it doesn't have any members in common with C, we get the class of C and D, also known as just C. For number 14, the union of A and D is B, C, D, E, F. If we subtract out B, so we subtract out the members of B, that's E and A. We didn't have any A's, but we had an E. We get B, C, D, F. Note that because A isn't a member of the union of A and D, we don't subtract it out, despite the fact that all of the members of A are in there. Next up, we have the intersection of A and B unioned with the difference between B and D. So the intersection of A and B is going to be the null set. They don't share any members. The difference between B and D is going to be just A, because we take B, we subtract out anything it has in common with D, so we take out the E. We're left with the class of A. So the union of the null set and the class of A is simply the class of A. And finally, the union of B and D minus the union of C and D, we get the union of B and D is going to be AEF, and the union of C and D is going to be CDEF. We take AEF and we subtract CDEF. We take out the E and the F, and we're left with just A. So our answer is the class of A. Whew! These exercises are getting more complicated. Watch this video and more here at Carneades.org. Stay tuned for a brand new video every single day this month on set theory. And stay skeptical, everybody.